残酷な天使のように少年よ神話になれ青い風が今胸のドアを叩いても私だけをただ見つめて微笑んでるあなたそっとくれるもの求めることに夢中で運命さえまだ知らない痛いけな瞳だけどいつか気づくでしょうその背中には遥か未来目指すための羽があること残酷な天使の手で窓辺からやがて飛び立つほとばしる熱いパトスで思い出を裏切るならこの空を抱いて輝く少年よ神話になれ
Shh, we're doing calculus. Okay guys, what's up? We're back talking about the fundamental theorem of calculus, which we learned about in the last video. So, let's quickly refresh our memory. Let's talk about the fundamental theorem of calculus, and then let's jump into it and do a whole bunch of examples. It's going to be fun, it's going to be cool, it's going to be great, you're going to love it. So, fundamental theorem of calculus, very important, so important that it came with two parts, which really say kind of the same thing, but just in different ways. So, part number one of the fundamental theorem said that if you had f, a continuous function on a closed interval from a to b, then the area function, which we're going to denote by a of x, and we define it as the definite integral from a to x of f of t dt, and of course this is only defined when it, makes sense for our purposes on the interval where our function is continuous, so for x between a and b. This area function is also continuous on that closed interval, and then here was the big part. Here was the big and cool part that made all of this worthwhile, because so far this is pretty expected. You've got a continuous function, you've got a function measuring the area under the graph of that function, measuring the net area under the curve for this function, and it's also continuous. That's not crazy. The crazy part is that the area function is differentiable on the closed interval from a to b. That's cool. We just started with an arbitrary continuous function and we got back a differentiable function. That's neat. Okay, cool. So, the best part though was that the area function is an antiderivative of the original function. So a prime of x is f of x. Or if you want to write it a little bit fancier, d dx of the definite integral from a to x of f of t dt is f of x. Cool. Okay. This says that continuous functions are derivatives of area functions. All of them. That's all they are. Cool. The second part took it kind of the other direction. So part two of the fundamental theorem, we started with pretty much the same thing. We had f, a continuous function on the closed interval from a to b, and we took big F to be any, literally any one you want, choose any one you feel like, any antiderivative of little f on that same interval. Then what we got out was a way to compute definite integrals. What we found out was that the definite integral from a to b of f of x dx was just big F of b minus big F of a. Okay, cool. This meant that it was no harder to do a definite integral than it was to do an indefinite integral. That is, to do a definite integral, we just do an indefinite integral, and then we plug in two numbers. Neat. All right, Let's get to some examples. Okay, first example, example 5. We're going to evaluate the definite integral from 0 to 2 pi of 3 sine x dx, and to do this we're going to use the fundamental theorem of calculus. So, to start it off, the first thing we're going to do is really just compute an indefinite integral. So, if we computed the indefinite integral of 3 sine x dx, well, what we'd get out is we'd get 3 times the indefinite integral of sine of x dx. And if we integrate sine x dx, we're just getting a function whose derivative is sine of x. Now, cosine derives to minus sine of x, so we'll need to pick up a minus cosine here for our signs to work out correctly. And what we'll get is 3 times minus cosine of x. And if you simplify just a little bit, that's minus 3 cosine of x. All right, cool. So we could also just use the antiderivative rules that we saw before, but ultimately, same thing either way. So we found an antiderivative of 3 sine x. It is minus 3 cosine of x. And if I'm being fully correct all the way up here, I should throw plus c's. But what I'm really doing, and this is sloppy that I didn't write them there in the first place, but ultimately forgivable in this context, because what I'm doing here is I am choosing one of these infinitely many antiderivatives. Namely, I'm choosing the one where c is equal to 0. So in your scratch work, yeah, I guess if you want to be technically correct, you should probably write the plus c there. You should always, strive for technical correctness. But at the end of the day, I don't know why you'd pick anything other than c equals 0. It'll make your life harder. Just put c equal to 0, life will be simple. Okay, so now that we've got an antiderivative, using the fundamental theorem of calculus, the value of the definite integral is pretty easy to compute. So the definite integral from 0 to 2 pi of 3 sine of x dx is just that antiderivative evaluated from 0 to 2 pi. Okay, so what does this mean? Just remember the notation there. This evaluation bar, this bad boy right here, is telling us to plug the top number into the function, then plug the bottom number in and put a minus sign in between. So we get minus 3 cosine of 2 pi minus 3 cosine of 0. Just doing a little bit of evaluation now, plugging and chugging, we'll get minus 3 times 1 minus 3 times 1. So this is just minus 3, and then when you minus a minus, that's plus 3. And of course, this just equals 0. That's our final answer, 0 net area. This actually is pretty much exactly what you should expect if we just throw ourselves a quick little graph here. Think about what cosine looks like for one period. So, take a period of cosine, so from 0 to 2 pi, and what you'll see is something that looks like, and this is a poorly drawn picture, so there's 2 pi, and basically what we're seeing here is that the area above the x-axis and below the curve is the same as that little chunk that is below the x-axis and above the curve. So they cancel each other out. That's what this is telling us. That's what this is telling us. These guys and this guy, these all cancel out. All right, cool. So we got 0 net area, despite the fact that there actually is area under there. There's just exactly as much area above the x-axis as there is below. That's what this 0 here means. It's kind of intuitive. Cool. Next example. Okay, example 6. Here things are going to get a little bit more interesting. So we're going to evaluate the definite integral from 1/16 to 1/4 of the square root of t minus 1 all over t dt, and we're going to do this using the fundamental theorem of calculus. So when you first look at this, you might think, oh my god, there is no good way for me to deal with this weirdo function right in here. But all we have to do is a little bit of algebraic manipulation, and then we're going to be set. So first off, we're going to simplify the integrand. That is, we're going to simplify this little thing right here, the thing between the integral signs and the dt, the integrand. Okay, so to do this, we just break everything up. So square root of t minus 1 all over t, we break this up into 1 over the square root of t minus 1 over t. If you want to see this little step right here, really what's going on is I'm taking square root of t over t minus 1 over t, and then I'm noticing that this thing is equal to, well, that's t to the 1/2 all over t minus 1 over t. And t to the 1/2 over t, I just subtract. So this is t to the 1 and t to the 1/2. And what I'm going to get here is just, well, I will get t to the minus 1/2 minus 1 over t. And this is exactly the same as 1 over the square root of t minus 1 over t. So that's where this guy comes from. That's exactly the same as what I have right here. Cool. Okay. So that little step of algebra out of the way, that's messy, but a little bit of algebra. Ultimately what we got is we got t to the minus 1/2 minus t to the minus 1. Okay, cool. This is something that we can handle in terms of finding an antiderivative. We just use the power rule for integrals, basically. The backwards version of the power rule that we're all familiar with from differentiation. So finding an antiderivative just using the rules we saw before, doing an indefinite integral, an antiderivative of t to the minus 1/2 minus t to the minus 1 would be 2t to the 1/2 minus natural log of t. So really natural log of absolute value of t, since we're only throwing in positive values in here, you know, both those numbers are positive, we are perfectly justified in just writing natural log of t instead of throwing the absolute value, but we'll put it there just to be very technically correct for the moment. So, using the fundamental theorem of calculus, we can evaluate this definite integral very straightforward. So the definite integral from 1/16 to 1/4 of square root of t minus 1 over t dt is that antiderivative we found, 2t to the 1/2 minus the natural log of t, or natural log of absolute value if we want to be totally specific. And we're going to evaluate this from 1/4 to 1/16. This just means we plug in the top number, and then we plug in the bottom number, we do a little bit of subtraction, and we're good to go. So we get 2 times the square root of 1/4 minus natural log of 1/4 minus the whole quantity minus the quantity 2 times the square root of 16 minus natural log of 1/16. Okay, cool, easy enough. Now all we got to do is a little bit of simplification. This is just pretty much arithmetic at this point. So square root of 1/4 is 1/2, so we get 2 times 1/2 from that square root of 1/4 times 2. Okay, and that just turns into 1, of course. Natural log of 1/4, I'm going to leave that exactly the same for now, and I'm just going to bring this minus sign on through, so that 2 times the square root of 1/16, just because the square root of 1/16 is 1/4, turns into 2 times 1/4, and that minus carries through, so I get minus 2 times 1/4. And just bringing this minus on through, I'll pick up a plus natural log of 1/16, which I'm not doing anything to quite yet. Okay, now I can do a bit of simplification. So what's going to happen next is that 2 times 1/2, that turns into 1 like we said before. I got that minus natural log of 1/4, I got that plus natural log of 1/16, and 2 times 1/4 is 1/2. It's got a minus in front of it, so I'm subtracting off 1/2. So 1 minus 1/2 is 1/2, and natural log of 1/16 minus natural log of 1/4 is just, well, it turns out to be minus natural log of 4. You could really just leave it how it is. You could just leave it as minus natural log of 1/4 plus natural log of 1/16, but we can simplify it down a little bit. Good chance to review some log properties. So how do we turn it into minus natural log of 4? might seem a little bit amazing at first, but the entire thing there to remember is that there are a lot of properties involved with natural logs and with logarithms in general that we can take advantage of to reduce expressions. So just really quick off to the side here, let's do a little tiny bit of scratch work. So what we have is we have natural log of 1/16 minus natural log of 1/4. Now what I can turn this into, if you recall some of our properties of natural logs, is just, well, I can turn this into, here I'll even write this vertically right here since I didn't quite give myself a lot of room, but whatever. It won't be a long calculation. It'll just be a natural log of 1 minus natural log of 16 minus natural log of 1 plus natural log of, well, 4. So this is a minus, and really what I'm picking up is this thing minus that thing. But if I want to keep things simple, I can just carry that minus on through. And hey, next thing you know, natural log of 1 minus natural log of 1, they cancel out. And I've just got natural log of 4 minus natural log of 16. And since natural log of 16 is just natural log of 4 to the second, I can just pull out this 2 and get natural log of 4 minus 2 times natural log of 4. And hey, that's minus natural log of 4. Bam! That's exactly what I picked up right here. All right, cool. So that's what I pick up over here. And if I punch this in a calculator, reduce things down a bit, this is something in the vicinity of minus 0.8863-ish. All right, so weird looking definite integral. A little bit of manipulation with logarithms. Realistically, you could just end it pretty much right here. Actually, once you're at this point, you've got your answer. There's just a lot of easy simplification you could do first. But once you got a number, your answer is equal to the right answer, and there's only arithmetic in between. You've pretty much got it. You could just throw it in a calculator if you want an approximation. This is a good enough exact form. If for some reason you want to reduce it down, probably the simplest one you can really get to is 1/2 minus natural log of 4. But there you go. Either way, you're set. Next example. Okay, cool. Example 7. Let's mix it up a little bit. Let's use part 1 of the fundamental theorem of calculus. So if you see something like this, at first it feels intimidating. At first it feels like, oh my God, how can I even deal with it? So it's actually a good thing. The best part is that when you see something like this, despite the fact that it looks terrible, you should actually kind of celebrate a little bit, because this is about the easiest problem you can possibly get. So we're going to use the fundamental theorem of calculus to simplify the expression d dx of the definite integral from 1 to x of sine squared t dt. So we're taking a derivative of an area function. What does part 1 of the fundamental theorem of calculus tell us? It says that the derivative of an area function is the original function. So I am taking the derivative of the definite integral from 1 to x of sine squared t dt. Part 1 of the fundamental theorem of calculus, get ready, this is easy, says that this is just sine squared x. Whoa, very nice. So basically the gist of it is that if you see a d dx, and then you see a definite integral of some function with an x up in that little top part, all you got to do, as long as you've also got a number in the bottom part there, all you've got to do is just take the function, write it down, and then replace whatever that variable there, that dummy variable, here we've got a t is, with x, that thing up top. All right, very easy, very convenient. That is about as simple as it goes. That is just part 1 of the fundamental theorem of calculus directly applied. No extra computations necessary. All right, cool. Next example. Okay, example 8. We're going to use the fundamental theorem of calculus to simplify the expression given by d dx, the derivative with respect to x, of the definite integral from x to 5 of the square root of t squared plus 1 dt. So, to apply part 1 of the fundamental theorem, what we need is that the variable of integration has to appear in the upper limit. The variable of derivation has to appear in the upper limit. Whatever thing I'm deriving with respect to, here it's x, has to be the upper limit of the integral. It has to be up top. But here I've got a 5. So, to put it in the right form so we can apply this, what we need to do first is just flip the bounds of integration. Luckily, we already know how to do this. When I flip my bounds of integration, I just pick up a minus sign. I'm just going the backwards direction, so I pick up a minus sign. I'm going towards the negatives now, and I pick up a minus sign accordingly. All right, so the definite integral from x to 5 of the square root of t squared plus 1 dt is just minus the definite integral from 5 to x of the square root of t squared plus 1 dt. So all I do is I pick up a minus when I flip the bounds. Now I can apply the fundamental theorem of calculus. So the thing I started out with, d dx, the derivative with respect to x of the definite integral from x to 5 of the square root of t squared plus 1 dt, I just use the fact that I can turn this into this equivalent form, and I pick up a minus, I carry it on outside, and I get minus d dx of the definite integral from 5 to x of the square root of t squared plus 1 dt. So this guy right here, this is a prime candidate to apply the fundamental theorem of calculus, at least part 1. So I'm taking the derivative of an area function. All I do is I take that function inside, the integrand right there, and I rewrite it now with x's instead of the dummy variable. In this case, that's t. But I've got a minus sign out front here, so I pick up that minus sign, and my final answer is minus square root of x squared plus 1. Pretty cool. All right, let's do another one. Okay, so let's finish it off strong with a pretty interesting example. Let's do example 9, where we're going to use the fundamental theorem of calculus to simplify the expression d dx, the derivative with respect to x, of the definite integral from 0 to x squared of cosine of t squared dt. Whoa! This is not something where we can directly apply the fundamental theorem of calculus without a little bit of extra effort. So the whole thing here that we need to notice is that the upper limit in the integral is not x, but is instead a function of x. So the function that we're differentiating is a composite function. That is, this guy here, it's almost an area function. It looks like an area function, but it's not quite. This function here is a composite function, or at least we'll want to treat it as a composite function, as a composition of two functions, to deal with this nicely using the fundamental theorem. So to do this, what we're basically going to do is we're going to take the thing that causes us trouble and we're going to relabel it and pretend it didn't. So this is a very common trick in mathematics, but ultimately all it really boils down to in this case is an application of the chain rule. That is, we're just going to let u equal x squared. Basically, we're saying, hey, I've got an integral from 0 to x squared of cosine of t squared dt, and what I want to have is just an x up top, but I don't. So instead, I'm just going to make this thing equal to u. Now, what I'll do here, what I have to do when I do the chain rule, is I have to accommodate this relabeling. So this is going back a little bit. We haven't talked about the chain rule in a while. If this is a bit rusty, don't worry. All we're really going to do here is we're going to say, hey, instead of writing this as a function of x, we'll write this as a function of u. So instead of having y equals this thing, instead I'll take y to be a function of u. Let's call this thing g of u. So we'll say g of u is equal to the definite integral from 0 to u of cosine of t squared dt, and we've got u set equal to x squared. Okay, Ultimately, we've recovered exactly the same function. We've just labeled things. We've split it into some chunks using the operation of composition. So when I differentiate this guy, I have to use the chain rule. This might be a little bit complicated when you first look at it, but let's just run through it together. So I'm taking the derivative with respect to x of the definite integral from 0 to x squared of cosine of t squared dt. This is dy dx if I let y be this thing, where u is equal to x squared. I've just relabeled some things. Using the chain rule and using the nice fact that up to relabeling, derivatives kind of work like fractions, dy dx is just dy du times du dx. Now the nice part here, this is what's going on between this step and this step, is that dy du is just d du of y. That's what this here means. It's just a fancier way of writing it, a more convenient and compact way of writing it. But notice d du of y, just using the fact that y here is equal to this bad boy here, gives me d du of the integral from 0 to u of cosine of t squared dt. So now that's what I've got down here, this first part right there. And then the other part is the du dx. So since u is equal to x squared, what I'll get out when I take a derivative with respect to x is really easy. I just use the power rule and I get 2x. Okay, so I picked that up right there. Nice. Now, since I've got d du of the integral from 0 to u of cosine of t squared dt, this is exactly what I could use the fundamental theorem of calculus part 1 on. Now I've got u's instead of x's. This isn't a problem. Remember, variables, the letters here, they're just symbols. You could use any old symbol you want. If you replace all of the x's with u's, it works the same. So what I pick up from this is just cosine of u squared. That is, I take the integrand and I replace the dummy variable, here it's a t, with the variable of derivation, the independent variable. That's u. So cosine of u squared times 2x is what I have, and just replacing u with what x is, I'm all good to go. So I have 2x, I'm going to write that in front just to make our lives easy, and then cosine of u squared turns into cosine of x squared squared. So x squared, if I square that, I have x squared times x squared, that's x to the fourth. So I get 2x times cosine of x to the fourth. And that is my final answer. So you can even apply the chain rule here. It looks a little bit messier, it looks more complicated, some of it looks very tricky to deal with, but it's really not. You just need to pause for a second and say, hey, just because I'm putting the variable for my function up in an integrand, nothing has gotten harder. I've just put the variable in a different place than I'm used to. It all works the same, it's just in a slightly different place. So all we do is just apply the good old-fashioned chain rule and we get our answer. The derivative with respect to x of the definite integral from 0 to x squared of cosine of t squared dt is just 2x cosine of x to the fourth. Cool, easy enough. We got some good practice with the fundamental theorem. There's a whole lot more things you can do. There's loads more examples. If you feel like you need some more practice, just sit down and try to come up with a few. Coming up with your own example problems is honestly some of the best ways you can study that there are. But that's what we got for today. Have a good one. Cool.
It is the 41st millennium. For more than 100 centuries, the mathematical emperor has sat immobile on the golden throne of Earth. He is the master of mathematics by the will of the gods, and the master of a million worlds by the might of his inscrutable theorems. He is a rotting carcass, writhing invisibly with power from the dark age of mathematics, the carrion lord of theory, for whom 1,000 lemmas are proved each day, so that he may never truly die. Yet even in his deathless state, the mathematical emperor continues his eternal vigilance. Mighty theorems are proved in the demon-infested miasma of academia, the only route to publication, their way lit by the emperor's own peer review, the psychic manifestation of his will. Vast armies of graduate students give battle in his name on uncounted worlds. Greatest amongst his protégés are the Adeptus Mathematicus, the space mathematicians, bioengineered super academics. Their comrades in arms are legion, the imperial proofreaders and countless planetary textbook authors, the ever-vigilant Inquisition and the category priests of the Adeptus Theoreticus, to name but only a few. For all their multitudes, they are barely enough to hold off the ever-present threat from academic dishonesty, less than total generality, heretics, plagiarists, and worse. To be a mathematician in such time is to be one amongst untold billions. It is to live in the cruelest and most theoretically rigorous regime imaginable. These are the tales of those times. Forget the power of technology and science, for so much has been forgotten that was not math, never to be relearned. Forget the promise of progress and understanding, for in the grim, dark future, there is only math. There is no English or humanities or sciences amongst the stars, only an eternity of proofs and theorems, and the laughter of thirsting gods.